we're going to look at diode circuits that provide either logic functions, which can be done with ideal or non-ideal diodes, and a few other circuits that just talk about how we solve them using ideal diodes. So for logic gates, actually diodes were used for logic gates before transistors were available. So the early logic gates were actually made out of diodes. And for some types of applications, they're actually still used because they can have different kinds of ways of handling signals versus those tiny little chips that you go get that have the whole gate on a chip. So for diode logic circuits, we make an assumption. We assume that logic 1 is +5 and logic 0 is 0. There's a 0 missing there, so that should be 0 right there. Don't know where that went. And we're going to make the assumption in this particular part that the diodes are ideal, which means that the voltage is 0 for forward biased and the current is 0 for reverse bias. So this is what the process is to analyze circuits with diodes. And actually this applies to non-ideal diodes as well. So any diode circuit, but we're going to start with ideal ones. Analyzing them requires making assumptions. Nobody likes making assumptions because assumptions are assumptions. You make your best assumption looking at the circuit as to whether the diodes are forward or reverse biased. You can look at the amount of voltage behind and in front. You can use a lot of different ways of thinking about it, but you make an assumption. It's like, okay, this diode's on, this diode's off, the one in the middle, that's on also. Then you redraw the circuit and replace on diodes with a short circuit and off diodes with an open circuit and analyze it. So we make the assumptions, we redraw the circuit, then we analyze the circuit and figure out what the node voltages are in that circuit. There might only be one that you need to find. There might be more than one. Once that's done, then you look and you see if KVL and KCL and what you know about diodes works. So in other words, if you look at the new circuit and you've said, okay, this diode is reverse biased, but then you notice that it actually has a voltage at the back and the front which would cause it to be forward biased, then your assumption is not correct. So you have to go back and reassess the circuit. And then once you do that, you basically see if KVL or KCL is violated at any point, which also, if you make invalid assumptions, you'll find that things don't add up properly. And that can also be a red flag. If that's determined that the state of the diodes is not correct, basically you go back to the beginning, make new assumptions, and do the whole circuit again. Yeah. Kind of. Although what happens is that when you've done enough of these, you can kind of look at them and know and make a pretty good first guess. When I go through and do examples, I'm going to pretend that I know nothing about this and just go and, make determinations and go through it logically. But usually, once you've done enough of these, you can figure them out. So first of all, logic gates. This works as an OR gate. And if any one of those inputs is +5, then the output is +5. And basically, pretending like you have 5 and 0 and 0, the 5 would forward bias this one, which means because it's ideal, you add 5 volts there, and then these two would be reverse bias because of the 5 volts, and V out would be 5. So any of the 5s coming into there makes the output 5. The only way to get an output of 0 is to have all the inputs be 0, because then all of the diodes are going to be basically off or Actually, they can all short circuit because there's no voltage at the other end. So either way, that's the only way that you can get an output that is a 0. So that's basically how you make an OR gate out of diodes. And this gets more complicated if you have different voltages going in. So you could have a situation, and I think there's a lab where you do, or maybe I'm remembering wrong, where you might have 6 volts, 12 volts, and 0 volts. And then you have to figure out which diodes would be forward biased and which wouldn't. So it's a little more complicated. But that's not technically an actual gate. That's more of an example in a circuit. So you can do that with an OR gate. You can also make an AND gate. And in this case, all of the input voltages have to be 5 to get a 5 out. So if you had 5 volts, 0, and 0, the voltage here would have to be 0, and that would mean that this would be reverse biased, and forward biased, and you would get an output of 0 as long as any of the inputs is 0. So to get a 5, you actually have to have all 5s going in, and then that will give you a 5 going out. So that's really, 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 really easy. We're going to look at some circuits that are actually actual circuits to kind of see how the process would go with a real circuit and how you would figure out which diodes were off and which diodes were on. So the first example we have is 2 diodes, 2 voltage sources, and 2 resistors. And we want to find V, which is the voltage between that pin going out and ground, and we want to find I, which is the current through diode 1. And basically, for this example, I'm just going to assume that I don't know anything about diodes and just make guesses. So the first guess I'm going to make is that both of the diodes are off. That's going to be my first guess. If they're both off, that means they're both open circuits. And that really doesn't work. Yeah. Well, nope, you have 10 volts here, and you have minus 10 here, and you have 0 up here. So really that doesn't work with reverse bias diodes because there actually is a voltage drop across there, and there actually is a voltage drop across there. So we can't. Now, we could jump and assume that they're both on, but we're not going to do that yet. We're going to go and actually, oh yeah, I did that. That's cool. I actually did that. That's nice. Sometimes I forget what I do. So off is off the table. That doesn't work. So, darn, yeah. It's nice when you get it right the first time. So the next thing we're going to try is D1 being on and D2 being off. So when we do that, D1 is a short circuit and D2 is an open circuit. And then we look at where the voltages are in this circuit, and we have 0, which that's okay. And then we have plus 10 and 0 across that gap, which again doesn't work. So that's not going to work either. So then we will go to the next example, which I'm going to switch them and do an off and an on, even though you guys know what the end of the story is going to be. It's not always like this. So this time we turn off D1, we replace D2 with a short, we look at where the voltages are, we actually calculate the voltage at V because now you've got a series circuit, and the voltage at V is minus 3.33 volts, which puts it right there. And if it's there, that means you still have a forward voltage across D1 because you've got 0 at the back side and negative 3.33 at the front side, so that still produces a voltage drop. So again, that one doesn't work either. So we're going to go to the last, which had better work, because if it doesn't, then we're out of options. So we're going to assume they're both on. We replace both with short circuits, and then we go through and we know that the value of V is actually 0 volts because there's a short between ground and that point goes all the way out to V. So that whole area is actually 0. So 0 volts for V, and then we're going to figure out what I is. by basically looking at the current, we know that 10 volts divided by 10 kiloohms is 1 milliamp, and there's nothing going off to that wire. So we got 1 milliamp going that way. And then 0 minus 10 over 5 gives us 2 milliamps. So we end up with a current for I of 1 milliamp. So we got a reasonable solution. It worked. And that's it. So what happens? Yes, go ahead.
Explain again why V is 0.
Yes, because the 0 basically is shorted through here, and then that whole node is 0. So that's basically what we end up with. Now all I'm going to do is I'm going to switch the two resistors. That's it. That's all I did. Switching the two resistors, we already know that off-off isn't going to work. It didn't work last time, and this circuit isn't that different, so off-off doesn't work. On-off is basically a similar situation to what we had before, where we ended up looking at the circuit and we turn it off, and then we end up with minus 10 here and 10 up here, so that still doesn't work. But I'm not going to assume that on is the answer as yet. I'm actually going to go and look at off and on. And when I do that, I'm going to get rid of this is where I get into trouble sometimes trying to use the eraser, but I'm going to try to use the eraser here. Yeah, great, I did it. Okay, so now that I've got off and on, I have a series circuit, and I can figure out what the voltage at V is. And when I do that, I get 3.33 volts. So because I get 3.33 volts, that diode D1 is actually not forward biased. It actually does work, it being reverse biased. So that's why you can't always assume, oh, I know what it's going to be because the last circuit showed me that it would be forward biased. So in this case, D1 is off and D2 is on, just because of the movement of the two resistors, and the current I is just going to be equal to 0 because there is no current in that open circuit. So there's going to be more of these you get to try on Friday. So it's maybe like 4 of those you get to try. So the last thing I'm going to say is just a very, very, very super brief, because I didn't know where to put it in the lecture structure, so I decided to put it here. And I'm just going to tell you very briefly about some other kinds of diodes that exist in the world. First of all, Schottky diodes. Schottky diodes are made out of a metal semiconductor junction, and they have a lower turn-on voltage than silicon diodes. They're like 0.3 to 0.5, 0.3 to 0.5 volts. Sometimes they can be used. Basically, they don't. Listen, what I'm trying to say about this, I don't know. I just suddenly thought of something else totally unrelated to what I'm talking about. Anyway, they switch on and off really fast, and the reason they do is because of the metal semiconductor junction. It actually, there's a different type of carrier that is being used for that junction versus a PN junction, so it switches back and forth much, much faster between forward and reverse biased. And then the lower voltage drop can be good as far as when you are using them in a circuit. So that's one type of diode that one might come across. Another kind is a varactor diode, and a varactor diode is basically used in its reverse direction, and it acts like a capacitor. It's actually a voltage-controlled capacitor. So the voltage can be adjusted, and that ends up changing the value of the capacitor. So it can be used if you need an exact value of a capacitor. If you're trying to tune oscillator frequencies and you're trying to make it an exact value, because capacitors, you know, don't come in too many values as standard values. They're really far apart. They're not real accurate. They can widely vary. So this makes it possible to actually tune a capacitor to an exact value. So that is, and when you are using LT Spice, I think when you type in V for voltage, you get this first. You have to type VO for a voltage source. This is what you actually get before you, that's what pops up when you're trying to find the voltage source. And then the last type is what's known as a photodiode. And actually, a photodiode is used for taking in light and producing electricity. So it uses whatever light is coming in, and then it causes current to flow, and you see them everywhere, light sensors, anything that's kind of sensing light and reacting to it. It's kind of the opposite of a light emitting diode, since a light emitting diode, which I didn't put on here, emits a photon when it has a certain voltage across it. So, or current through it usually is more what it does. But a light emitting diode does the same kind of thing where it has current going through it, and the amount of light that is emitted is directly related to the amount of current that's going through it. Photodiode, exactly the opposite. It takes in light and it produces a current based on how much light it sees. Silicon doesn't work super well for this kind of diode, either light emitting or light absorbing. Gallium arsenide works better because there's enough energy, basically because it's a direct band gap semiconductor. If you've ever taken 2401, the electrons going from the valence band to the conduction band go in kind of a straight line, and so there's enough energy left to emit a photon. With silicon, it's actually indirect, and it has to travel this way. It changes momentum, that uses energy. It can't emit a photon. So those are the kinds of diodes that might come up in your life one way or another. That's all I'm going to say about this part of diodes.